All right, my name is Lorien Wheeler. I work on the Asteroid Threat Assessment Project at NASA Ames, and I'm going to give a lightning fast overview of the hypothetical asteroid impact exercise that my co-authors, Jesse Dotson, Paul Chodas, and Brent Barbie and I performed for this year's Planetary Defense Conference. There were many other people who contributed to this exercise. They included several groups supporting NASA's Planetary Defense Coordination Office, along with many other organizers and panelists from ESA's Planetary Defense Office, IWAN, Same Page, UN-USA, and others. So first, to give some quick background, these exercises role play through a realistic but fictitious asteroid threat scenario. The scenario is planned and assessed in advance to demonstrate key aspects of the discovery, observation, risk, and response options. The available information is then presented to the conference in several injects, which represent different times during the asteroid's approach. The purpose of these is to test and stretch our current assessment tools and processes and to identify any key gaps or advancements. Doing this as part of an international conference like PDC also helps raise awareness of the need for planetary defense generally and enables collaboration among the many groups studying different aspects of the problem. So this year's PDC exercise was designed to be a short warning, mid-size impactor scenario. The intent was to emphasize the need for NEO discovery assets, rapid response mitigation, and also disaster planning. The scenario was presented in 4 injects. There were 2 more extensive updates on days 1 and 3, plus 2 mini updates on days 2 and 4. These maps here show the evolution of the potential impact locations across the injects. Day 1 covered the initial discovery and risk assessment just 6 months before the potential impact. At that point, there was only a 5% chance that it would hit Earth, and the potential impact location spanned 2/3 of the globe. On day 2, 1 week after discovery, an assessment of the mission options showed that no missions could be launched in time. Orbit refinements based on a pre-recovery of the object in archival images then confirmed that the object would indeed hit Earth somewhere over Central Europe or North Africa. Day 3 then advanced us to 4 months before the impact, when the potential impact location was narrowed to somewhere over Central Europe, and a weak NEOWISE detection reduced the upper end of the asteroid size estimates. At this point, we knew that no mitigation was possible, and so disaster response planning was definitely needed. Day 4 closed out the scenario with just a brief update on the final damage region estimates 6 days before impact, when Goldstone radar was able to refine the asteroid size to within around 10%. So assessing potential impact threats for scenarios like this involves many unknowns, such as if and where the asteroid could strike Earth, its size and physical properties, and how much damage it could then do. So to assess the risk posed by these kinds of scenarios, we have a probabilistic asteroid impact risk model. It uses fast-running physics-based models of asteroid entry and damage to assess millions of cases representing the range of these unknown factors. The asteroid properties are first sampled from distributions based on general asteroid characteristics, along with any observational data for the particular object. The impact locations and probabilities are provided by the CNEOS orbital modeling. For each case, the entry and breakup is modeled to estimate airburst altitudes or surface impacts, and the resulting damage is then modeled for various hazards. These include blast damage, thermal damage, tsunami inundation, and global effects for larger impactors. And finally, the world population data is used to estimate the number of people affected locally for each case, and the results are all aggregated to determine the total probabilities of various damage levels. So here we have an overview of the impact risk assessment that we performed for day 1 of the scenario based on the minimal information available from the initial object discovery. At this point, as I said, there was only a 5% chance that the object could strike Earth in 6 months' time, and the only available property measurement that we had was an H magnitude estimate of 22.4. Given the uncertainty in H, albedo, and the other properties, the asteroid diameter could range from 35 to 700 meters, and the impact energy could range from around 1 megaton to 13 gigatons of TNT equivalent. The distributions skew more towards the smaller ranges, however, so the average sizes are around 150 meters or 250 megatons, and the largest sizes are much more unlikely. For these size ranges, the primary hazard is blast overpressure from an airburst or impact. Blast damage could range from minor structural damage to unsurvivable devastation. And the damage areas could extend out as far as hundreds of kilometers in radius. And depending on where the damage occurs, it could affect up to tens of millions of people. However, there's also a 97% chance that there will be no damage if the asteroid either misses Earth or strikes somewhere unpopulated, or is just small enough to do very little damage. The map here shows the average affected populations across the potential impact entry locations, and the histogram on the bottom shows the total affected population probabilities. The upshot is that at this stage of the scenario, we had a very challenging level of uncertainty for decision makers, combining a high likelihood of no damage with a small chance of very catastrophic damage, which could threaten almost any region of the world. So moving on to day 2, Brent Barbie presented an assessment of the mission options for the scenario, given the object's orbit, the 6-month warning time, and current launch and spacecraft capabilities. The primary finding was that we don't currently have rapid launch capabilities that would realistically be able to get a spacecraft to the asteroid on short notice. However, the assessment did evaluate the missions that would have been possible if rapid launch were available. So for this scenario, deflection of the asteroid was not practical due to the short time frame, and the best mitigation option would be disruption with the largest possible NED that could be delivered. Recon missions could also be possible, but the short time frames would require really challenging fast flyby trajectories rather than rendezvous options. I'd also like to note that raising awareness of the gap in rapid launch capabilities here was an intentional part of doing this short warning scenario. A bunch of the media coverage really enjoyed dramatizing this and something along the lines of experts fail to save Earth, or there's no technology in existence to save us. But it was actually a planned feature, not a bug. So we also then evaluated how much the hypothetical mission options could have reduced the impact risk or damage uncertainties compared to the initial day 1 risk results. The histogram on the left shows the reduction in the affected population risk provided by a disruption mission delivering the largest possible NED. Given the uncertainties in the asteroid size and density, 64% of the potential objects could be successfully disrupted. This would then reduce the total chance of any population damage occurring by around 57%. If we instead just sent a recon mission to better determine the asteroid size, this would also provide a notable benefit in reducing the uncertainty in the potential damage areas for disaster planning. The histogram on the right here shows a sample comparison of the damage radius probabilities with and without a recon mission that could hypothetically measure diameter to within 10%, assuming a sample median object size. For day 3 of the exercise, we performed an updated risk assessment using the information available 4 months before impact. The marginal neowise detection that I mentioned earlier reduced the low probability largest size estimates down to around 500 meters or 3,700 megatons. But we now had a certain impending impact somewhere over Central Europe. So whereas before we had a high probability of no damage along with a small probability of large damage, we now had a situation with damage very likely to affect hundreds of thousands of people or more. The worst case damage had decreased substantially from the initial tens of millions of people now down into the millions, but there was also no longer any chance that the asteroid would miss Earth or strike an unpopulated area. So the average affected population increased by an order of magnitude, and the most likely range was in the hundreds of thousands. So since no mitigation was possible, the scenario now became a short warning emergency response situation. As a result, the day 3 risk briefing focused on potential ground damage, severities, and sizes. So here we have the damage risk swath for day 3. This map shows the full range of potential regions potentially at risk to different damage severity levels. It covers all potential impact points and all potential damage sizes, including the very unlikely maximum size cases. Excuse me. The overlaid rings show the more likely average damage footprint sizes located over several of the major cities within the swath. These average damage radii range from around 10 kilometers for the highest unsurvivable levels out to around 80 kilometers at the lower serious damage level. Because the asteroid's size and properties were still very uncertain, there was also a very large range in the potential ground damage, with the largest regions being up to around 250 kilometers in radius. Because of this, disaster response plans would need to consider the relative likelihood of the potential damage in determining how best to evacuate or protect different regions. So here we showed examples of the range of damage sizes at a sample point near Vienna. The percentile sizes along the bottom indicate the likelihood that the damage would be smaller than the given size shown. For example, looking at the 75th percentile footprint here, if responders were able to evacuate a region out to 120 kilometers, they would have a 75% chance of having covered at least as much area as needed, and a 25% chance that the actual damage may end up being larger. We also considered the worst case model that affected the greatest numbers of people. Even though it's unlikely, people always ask about the worst case, so we used it as a demonstration. Our model estimates different fractions of the population affected depending on the damage severity. And the greatest affected populations in this scenario were mostly driven by the larger, less severe damage areas rather than the smaller, more severe damage areas. Also, the very worst case was not centered over the highest population city along the swath, like you might expect, but instead it spanned multiple urban areas within the larger outer damage region. And finally, the exercise concluded with a brief update on the final damage risk region 6 days before impact. The entry locations were then very well predicted near the border of Germany, Austria, and the Czech Republic. And Goldstone had measured the asteroid diameter to be around 105 meters with a 10% uncertainty. This risk swath map again shows the full range of regions potentially at risk, given the largest possible damage radii of up to 130 kilometers, with average damage footprint sizes closer to around 70 kilometers, shown overlaid as empty rings. So in summary, this scenario provided a really good exercise of the assessment processes among the observing groups and risk modelers and mission designers. It demonstrated how early NEO detection, rapid launch, emergency response, and risk assessment are all key capabilities for planetary defense. On the observing side, precoveries in archival images can be a valuable resource for quickly refining impact probabilities and locations. With limited observing opportunities, the object size and properties can remain really uncertain even days before impact. So for risk assessment, these uncertainties then lead to very large ranges in the potential damage. The worst cases can be very large, but also pretty unlikely. Less severe damage levels extending over large distances could affect more people than the smaller, more severe damage regions. And because of all these factors, effective response decisions would need to be able to consider both the range and the likelihood of the potential outcome severities. In terms of the response options available, the scenario called attention to the fact that we don't currently have rapid launch capabilities ready to send any missions with this little warning. If rapid launch were available, however, nuclear disruption could mitigate a significant portion of the risk, and recon data would be a really good resource for estimating damage regions for the disaster planning. But without launch options, the scenario showed the need to have emergency response plans for potentially large uncertain regions. It provided a valuable awareness with disaster response groups. It showed the need for clear damage risk metrics that they could act upon, and also raised some of the important challenges in communicating these kinds of uncertain risks to the responders, to the media, and to the public. So that's my lightning fast summary of the exercise. For more information, Brent previously provided a lot of these links, but there is more information on the CNEOS website with all of the full risk briefing slides and recordings and a number of other media articles here. So that's all I have. I'm going to get out of presentation mode so I can see any chat, and I'll take any questions.
Thank you. There was a bit of discussion as your talk went on, but please take a look if you want to add further comments. Or I invite questions from the audience.
Hey, Lorien. I had my hand raised, but I don't think you can.
Yeah, I'm having trouble finding the relevant questions. Go ahead.
Just real quick, I just wanted to see, could you maybe expand on a little bit on what you mean by rapid missions? Because there's rapid and rapid, right?
So Brent might be able to better answer that question. He did all the mission assessment, but basically, given the 6-month warning time discovery, if we were able to launch under the assumption that we could launch 12 days, I think it was 12 days after discovery, and then still get a spacecraft to the asteroid with at least 1 month before impact, there would be trajectories available. However, we wouldn't be able to actually get a launch vehicle and spacecraft on the pad and launched in that amount of time, given the current launch infrastructure. Does that answer your question?
Yeah, I was for that scenario, but I was, yeah, I guess it does for a bit. I'm trying to figure out how, if there's another more granularity in terms of the rapid nature of a mission. So whether it's just launch vehicle or if there's something else in terms of the integration and you know, building the actual vehicle itself and then launching it. I'm trying to pull on that a little bit more.
I believe so. Brent's launch performance models did find trajectories that would launch within the time frame that I mentioned, but they would be challenging, sort of fast flyby with difficult phase angles. So it would be a challenging scenario, even given rapid launch capabilities.